Okay, this is number 2 from the 2013 AP Physics B exam. This problem is primarily going to be an energy-driven problem with some simple harmonic motion towards the end. We have a 20 kilogram box on a horizontal frictionless surface moving to the right with a speed of 4 meters per second. Box hits and remains attached to one end of a spring without any mass that we have to worry about. It's attached to a wall. It's going to compress that spring 0.5 meters and then basically oscillate back and forth. So A1, the spring does work on the box from the moment the box first hits the spring to the moment the spring reaches its maximum compression. What we want to know is the work done by the spring positive, negative, or zero. I'm going to draw this kind of a little bit just so we can envision what's happening. And you know, I don't have the greatest physics art skills. We have this box that is sliding to the right. And we have a spring waiting for the box to hit it. That's the first moment in time. So then the next moment in time, or not the next moment in time, but once the box, I do not like that line, I'm going to redo it. Once this box goes ahead and hits the spring will compress a certain distance. And I'm going to cheat a little bit by just copying and pasting it and manipulating my art. And so, at this point, the maximum compression is where the object stops. And there's no indication that there's any energy loss. So we're going to assume that everything here is transferred from one to the next or retained. So here we have motion, and so we have kinetic energy. And then here we have no motion, so all of that energy gets transferred. And it turns out it's being transferred as potential energy due to that spring. So we can call it elastic potential energy, either P sub S or P sub U or something of this nature works perfectly fine. And so in order for the spring to store it, it had to do work on the object to slow it down. And so we want to know, is that work positive or negative? And I think the best way of answering this is first of all, it's definitely negative. And how do we justify it? That's what I mean by the best way of answering it. You could say the spring was acting to the left, and the object was originally going to the right, so you can say it's negative because of that, but I don't really like directional stuff dealing with energy. I like to think of it as it took the energy away. So if it originally had kinetic energy and now it doesn't have kinetic energy, the negative work was done on it to reduce its kinetic energy. I think that's the best way of answering this one, so that's what I'm going to stick with. A1 was worth 2 points. 1 for the correct response, and 1 for a good justification. A2, we want to now know the magnitude of that work described, and as we already said, the work will actually end up equaling the initial kinetic energy, because work is change in energy. That's my favorite definition of work. And in this example, it's change in kinetic energy, which is technically 1/2 m delta v squared. Understand that final velocity is 0, though, so it's really going to also be equivalent to 1/2 v initial squared. And we're looking for the work, so it's already isolated. At this point, we just got to plug in our numbers. 1/2 of the mass of the block, which was 20 kilograms. Again, make sure you're plugging in units and or make sure you make a proper knowns list. And our change of velocity is -4. However, I'm not going to worry about the negative. I'm just going to utilize my words at the end for that. I'm just going to say it's 4 meters per second squared for now. And 4 squared is 16 times 1/2 of 20. We get 160 joules. Now, I'm a fan of notating sign using words. So rather than saying, oh, it's positive 160 joules or negative 160 joules, I would encourage you to write out the spring did 160 joules worth of work in stopping the box. Alright, A part 2. This whole thing was worth 3 points. So before we even get into some of this oscillating stuff, our first third of our points are covered in part A. And let me label that way if I need to refer back to it, I have it. So this is actually A2. Okay, part B. We want to know the spring constant of the spring. So if we once again look kind of back up in this diagram, we have original kinetic energy, and then work is done on it, and then it finishes potential energy. I want to take a look at this potential energy bit. Because while I know that potential energy is 1/2 kx squared, I also know that this has to equal the work done by the spring. It's that change in energy, which technically also equals that original kinetic energy, but we already have a value for work written down up here, so that's what I'm going to use. X is the distance the spring is compressed. It gave it to you. Pay attention to units. In this case, our units are fine, 0.5 meters. It's not in centimeters. So I just got to isolate K. K is going to be 2W divided by X squared. Please don't forget to carry that square over with it. A lot of students tend to forget that. 2 times 160 joules. That's the work we found up in part A. Let me toss my units in there. All divided by 0.5 meters squared. I think that, yeah, that ends up... I probably should type this in just in case. So 160 times 2. Divide that by x squared. And I'm going to get 1,280. 1280. And your units for spring constant is a Newton per meter. That's a positive value, it's a constant. Part B was worth 2 points. Alright, I'm going to clean this up, shrink it up, move it out of my way. I know you can't do that if you're doing this along with me. I am sorry. Well, I guess if you're doing this on a tablet or some sort of writing device, you can. Not a problem. Alright, C. We want to know the maximum acceleration of the box. If you think about it, that maximum acceleration occurs when that spring is completely compressed. Right when the box first hits the spring, at that instant it touches, there's no acceleration. And the moment he starts to compress the spring, there starts to be a force acting against it. And we get our largest force when the spring is fully compressed, which will be our largest acceleration. So, the solution to C is to recognize that the net force acting on the object at that spot, maybe a Newton's second law analysis, is ma. It's not 0. And it's equal to the one and only one force in that dimension of motion, which is the spring force. Which means the acceleration is the spring force divided by m. Well, the spring force is going to be kx. So your acceleration is kx divided by mass. Now there is potentially some directional information that you should include. I'll talk about that in a moment. Your K value is 1280 newtons per meter times your X value of 0.5 meters. You're going to divide that by the mass of the block, 20 kilograms. And we're going to get an acceleration here of 32 meters per second squared. Now, I am not going to encourage you to put directional information, i.e., I don't need to worry about positive or negative right now, for 2 reasons. One, it does say magnitude of acceleration. Magnitude implies all I care about is the value, not the direction. Second, this actually exists in two different spots. It does exist when the spring is completely compressed, and that means the acceleration would be to the left, which we would typically define as negative. But then it's going to oscillate back and forth, and eventually the spring's going to be completely stretched out, and then that acceleration is the same value but to the right. So don't stress about positive or negative here. I know a lot of equations for Hooke's law has negative kx there, and that's all directional. That negative is directional information. So as long as you understand the direction yourself, you're fine. All right, D. We want to now know, C was worth 2 points. Okay, now I'm going to do D. We would like to figure out the frequency of the box. Hopefully, you guys recognize that for that we're going to use one of our simple harmonic motion problems. Frequency is 1 over 2 pi radical k over m. Now you could remember the period version of this, 2 pi radical m over k, and just understand frequency is the inverse of the period, so we just flip it all upside down. At this point we have everything, we're just going to plug in 1 over 2 pi, just use the calculator button for pi instead of writing in 3.14. K is going to be the 1280 newtons per meter, divided by the mass, which is the 20 kilograms. We're going to get a value of 1.27 hertz. The unit for frequency of the hertz. You could write an inverse second and you'd get full credit still. Alright, D was worth 2 points. And now E, we have two different situations, or I guess two different graphs that we're going to be looking at or creating. And the first one says we would like to let the initial starting point of x being 0, which is the point where the box makes contact with the spring. We're going to treat x to the right as positive. And so on the axes below, we're going to sketch your kinetic energy as a function of time, or a function of position, going from the range of negative 0.5 to positive 0.5. So when the block has yet to hit the spring, that's where x is 0, and it's got our maximum kinetic energy. It's going the fastest. Then, once it compresses the spring completely at the positive 0.5 mark, we have no kinetic energy. It's going to oscillate back and forth, so on the opposite end, where it's completely expanded, we also have no kinetic energy. The only thing you got to catch here is that it's an exponential relationship, not a linear relationship, because I won't have kx squared bit. So I want to see a curve here, which I'm trying to do nice and accurately. That's fine. This one was worth 2 points. And finally, in our last step, we want to do the same idea, but let's talk about the acceleration instead. And so here, directional information will be important. First, when the spring isn't compressed at all, we have no acceleration because it's constant velocity. And if we think about it here, up earlier I said this too, when the spring is completely compressed, it's pushing to the left. So when it's at a positive 0.5, i.e. it has been pushed to the right, it's pushing to the left with the greatest acceleration or force possible. Then the block will expand back out to its maximum expansion, and that's where the spring's trying to pull the block back in. So we also have maximum acceleration, but positive. Lastly, you do need to recognize that this is a linear relationship. We do have that, well, F equals ma, kx, whatever direction you want to take with it, a linear change in acceleration, not exponential. And it's a sketch, so you didn't have to use a straight edge, but why not, right? And sometimes it's helpful to make sure you're aligning this up with a 0.5, so the answer key shows a dashed line here. I don't think that's necessary. And this whole thing was only worth 1 point. Now, this was a multi-part problem, but that's kind of beneficial. That means each part is only worth a couple points, so it's easy to kind of pluck away and get as many points as you possibly can on here. All right, that's it.